So this video is going to be on the ear, hearing and balance. It is chapter 15, lecture outline C, starting at slide 20. So the ear has three parts. There's the external ear, the middle ear, and the internal ear. We all are probably familiar with that. The external ear and the middle ear are only used for hearing. The internal ear is hearing and balance, equilibrium. Now, in the inner ear, there are receptors for hearing and receptors for balance, and they respond to different stimuli, and they are independent. They just happen to be in the same organ, but we can consider them as if they were completely independent. So, parts of the external ear, the auricle, the rounded part is the helix, the ear lobe, or lobule, the external auditory meatus is here. There's some cartilages that give it its shape. The external auditory meatus ends at the eardrum, the tympanic membrane. In the middle ear, there are three bones, the incus, malleus, and stapes bones. They connect the eardrum to the organ of hearing, which is in the inner ear. They act as a mechanical amplifier. They take the vibrations of the eardrum and they make them into larger vibrations here. There is a tube that equalizes the pressure to atmospheric pressure in the middle ear, so that it's the same as the external ear. So the helix and the lobule of the pinna, the external auditory meatus, there are hairs in it, sebaceous glands, ceruminous glands. Cerumen is earwax. The eardrum is the boundary between the external and middle. It is connective tissue. It vibrates in response to the air pressure of sound, and it transfers that sound energy into mechanical energy, mechanical movement of the bones of the middle ear. So the middle ear is air-filled, lined with a mucosa. It's in the temporal bone. The eardrum is on one side, and on the other side there are two windows in the bone, the oval window and the round window. We'll talk about them later. The area above is called the epitympanic recess. Literally means above the eardrum. The pharyngeotympanic tube is the one that goes down to the nasopharynx. So it enters in behind your nose, and it's used for equalizing the pressure. That's why if you block your nose and blow your nose, you will actually hear it. You'll feel the pressure against your eardrum. We used to call them the eustachian tubes. Okay, so the round window is basically a pressure relief. The oval window is where the stapes bone pushes into the inner ear. So when this goes in and out, the liquid in here goes under pressure when it goes in. Pressure is reduced when it goes out. It ends up making this bulge. So when that goes in, this bulges out. When that pulls out, this bulges in, and it keeps the pressures modulated. So the malleus is here, the incus is here, and the stapes is here. Their job, like I said, is to act as a mechanical amplifier. There are some muscles, the tensor tympani and the stapedius muscle, and it's to protect against loud sounds. They modulate, they turn things down. Again, this is kind of a bit of an angle, but you can see these. You can probably tense this. This is a voluntary muscle. You can tense it, and you can hear a sound when that happens. The muscles are suspended by little ligaments here. Okay, in the inner ear, there is something called the labyrinth. And these are channels within the temporal bone. And it's lined with this organ. And there's three parts to the organ: the vestibule, the semicircular canals, and the cochlea. The cochlea looks like a snail shell. It's filled with this fluid called perilymph, and inside is are sacs filled with something called endolymph. So the space in the bone is here, right? These are the semicircular canals. In here, it's filled with these ducts are filled with endolymph, and the space is filled with perilymph. We'll come back to this diagram a little bit later. So the vestibule is in the center of this organ. It's egg-shaped within the bony labyrinth, and there's two sacs in it filled with perilymph or endolymph. The saccule, continuous with the cochlea, and the utricle, continuous with the semicircular canals. And within these sacs, there are receptors called maculae, and they respond to gravity, and therefore changes in position of the head. If you tilt your head, the angle changes. There's three semicircular canals, one in each plane of direction. They're 2/3 of a circle. So there's an anterior one, a lateral one, and a posterior one. So there's ducts in them, right? And there's a little ampulla filled with liquid at the end of each one. And the receptors in these semicircular canals respond to rotational movements of the head, any changes of angle of the head. So the ampulla is here. There's the anterior, there's the posterior, and there's the lateral. Each one has their own ampulla, and each one of them has the Crista Ampullaris receptors, and you'll see that the nerve is attached to that. The saccule here also has an area called the macule here, and that's attached to the nerve. So this responds to rotational motion. This responds to gravity. The cochlea looks like a coiled up snail shell. There's the cochlear duct and the organ of Corti. And this is all about hearing. So there's the scala vestibuli, so that's right against the oval window, and there's perilymph in that. The scala media is also filled with perilymph. So then there's endolymph in the media, and the scala tympani terminates at the round window, and it's perilymph. So we'll look at this a little more closely. There's a cochlear branch of the vestibulocochlear nerve, and it runs from the organs back to the brain. So if we look at it in cross-section, we'll see that each one of these spaces has kind of got two little sacs in it. And I'm not going to get too much into it, but suffice it that liquid continues around like this. So perilymph, endolymph. These are the three parts. Okay. Now, in here, in the scala media with the endolymph, there are these little organs with hairs on them, and these hairs move in response to movement in the endolymph. See the little hairs? Now this membrane, tectorial membrane, overlies them. Right? These are just supporting cells, and it's all on a basal lamina here. Cochlear nerve. There's some outer hair cells and some inner hair cells. That's more information than you actually need, but nevertheless, it's there. Here's a photomicrograph of them, and they're called hair cells because they literally look like hair. So we're going to continue with part D, which is still about hearing. So what sound is waves in the air. So a sound wave is a sine wave. It's movement of air molecules in a rhythmic sort of pattern. And I'm not going to get into the properties that much, but the wavelength is the distance between the crests, right? The amplitude is the height of one between the top of the crest and the bottom of the trough. So frequency is the number of waves passing at a given point, and that's really a property of wavelength. So in sound, pitch is how you perceive the different frequencies, which is a property of wavelength. So if 20 pass per second or 20,000 pass per second, the higher frequency, higher the pitch. Right? Loudness is the perception of sound intensity. So long wavelengths, lower frequency, low pitch, high wavelengths, high, or short wavelengths, high frequency, high pitch. Low amplitude is soft sound, high amplitude, loud sound. These things tend to make that concept, which is a simple concept, more complicated than it needs to be. So the sound waves, the movement of air, hits the very thin eardrum, the tympanic membrane, and vibrates the tympanic membrane. Then the little bones vibrate and amplify the pressure. So a little bit of vibration of the tympanic membrane becomes significant vibration at the stapes at the oval window. And then that sets up pressure waves in the perilymph. Right? So I'm not really that worried about that, but here we go. So sound waves move the tympanic membrane, which then moves the stapes, which then moves the perilymph here. Okay, which then moves the round window. So this moves through the scala vestibule. Now, what ends up happening is that certain frequencies will then go into the cochlear duct in the center and vibrate that. If the frequency is too low or too high, it doesn't go through. It continues back around. Right. If it's just right, it sets up a vibration in the cochlear duct, which narrows, so depending on the diameter, that's the frequency that it resonates at. So so the resonating frequencies continue on. I'm not going to get into too much about it. So high frequency displace near the window. Low frequencies displace further out. So this would be that straightened out. So low frequencies cause a deformation towards the apex of it, medium frequency in the middle, high frequencies at the beginning. And so which hairs get vibrated depends on the frequency here. So long fibers are here, short fibers are there. High frequency makes the short, stiff fibers move, and you will then perceive it as a high-pitched sound. Low frequency makes the long fibers out here move, and you perceive it as a low-pitched sound. So there's the supporting cells and there's the hair cells in the cochlea. Again, same picture. We've seen this before. So the hairs are called stereocilia. They protrude into the endolymph. They end up in the tectorial membrane. When they move, they bend, they open mechanically gated ion channels, which then changes sodium and potassium and calcium and depolarizes and start a nerve impulse. Okay, so we're not really too worried about the auditory pathways to the brain beyond the most straightforward parts of it. So um, I don't really care that the superior ovulatory nucleus in the brainstem and the inferior colliculus, which means a little hill, um, are there. Yeah, that's the auditory reflex center. So that's where you get startled by sound. But it goes to the thalamus and then up into the auditory cortex of the brain. And the pathways from each ear go to both sides of the brain. So this is the pathway. So so each specific hair cell is a different pitch. And which hair cells are stimulated depends on the frequency and the wavelength of the sound waves, or by that point the mechanical waves in the perilymph and the endolymph. Loudness is increased frequency, so increased frequency of action potentials, because the hair cells get larger deflections, so therefore they will reach action potential more often. So comparing what your left ear hears to what your right ear hears in timing is how we determine location. So I'm not going to get into homeostatic imbalances because these things are the subject of pathology. Now, equilibrium happens much in the same way in the same areas, but different stimuli. So the vestibular apparatus is this vestibule and the semicircular canals. The vestibule is static equilibrium. Which way is up? Like it depends on gravity. The semicircular canals only work during movement. So if you nod your head forward and back like you're saying yes, it's the semicircular canals that are involved. If you lay down, it's the vestibular receptors that are involved. So the maculae is the part of the vestibule that has the sensory receptors for static equilibrium. So they monitor the position of the head in space, and it's for control of posture. So if you tilt your head to the left, then your left ear is lower than your right, and so different parts of each macula, left ear and right ear, will be stimulated, and your brain will interpret that as a position of the head. They have hair cells and supporting cells as well, and they have these things called otoliths, which actually gives some weight to the membrane. So it's kind of like the membrane in the hearing over the hair cells, except it's got these liths, these stones, and concretions that give it weight, so that when you are straight up and down, they push down on the hairs, and when you're sideways, they push sideways on the hairs because of gravity acting on the otoliths. Now, we make these in our inner ear, and we have them all the time. Other animals bring them from the outside. Like, for instance, lobsters and crayfish bring sand in from the outside, and they deposit it, and they do it at every molt. When I was in university, my professor had a bunch of crayfish in an aquarium in his office, that at the bottom of the aquarium he used iron filings instead of sand. Let them molt a couple of times, and then he would put a big magnet over the top, and all the crayfish would turn upside down because the magnet would override gravity, and the crayfish wouldn't know which way it was up. It was a very interesting demonstration of how this works. They still had the hair cells and had everything else, but the otoliths were iron for them. So the macula respond to the horizontal movements side to side. In the saccule, it's up and down. The bending of the hairs are the kinocilia. I don't really care that much about differentiating them, but what you end up is when the hairs move, it depolarizes the hair cell, which then releases a neurotransmitter, which then generates an action potential in the vestibular part of the vestibular cochlear nerve. If it bends the opposite direction, it hyperpolarizes, reducing the action potentials in that. So the brain can know the position of the head. So when it goes one way, depolarization and hyperpolarization. What that means is that when you tilt your head one way, like so if you tilt your head to the right, then you are going to get depolarization of the one side, and you're going to get hyperpolarization of the other, and your brain will figure that out, figure out what position that means that your head is in. So in the semicircular canals, there are sensors to movement. So here, we'll just look at the picture. So the endolymph is here, and these movements are encased in this stuff called the cupula. And as liquid sloshes through the semicircular canal, it deflects the cupula, which then affects the hair cells. So changes in velocity, rotation movements of the head slosh that liquid in the canal that is in the axis of that movement, bending the hairs, causing depolarization and impulses. So if it goes the opposite direction, you get a hyperpolarization. And again, the balance between hyperpolarization and depolarization, and the body figures it out. So if one ear is hyperpolarizing while the other one is depolarizing, then you know you're going that direction. If they are both hyperpolarizing, you know it's you're spinning. If you know, so it's the differences that matter, left and right. We're not so worried about the pathways. They're very complex. But there's an interaction between the vestibular receptors and the visual receptors and the somatic receptors. And the only reason that we're going to talk about this is because this is what leads to motion sickness. When you're riding in a car, especially in the back seat, what's happening is your visual receptors are saying the movement, there's a lot of movement that's happening quickly, and it's happening in a rotation manner. But the vestibular receptors are quiet, and so are the somatic receptors, because you're not moving, you're just sitting. And so your brain's getting two different types of information, and then that confusion leads to nausea. Seasickness is when the visual receptors are saying you're still, but the vestibular receptors say that you are moving. And probably, for that matter, the somatic receptors are sometimes are moving and sometimes aren't. So it's when the information doesn't add up is when you get seasick. Right. So this is all how it works. So that's it for hearing and balance. The developmental aspects we are not covering.